Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. So do watch this session. If you like it, do press the like button and share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. All right. You can also visit our website www.we-learning.in. You will be getting all these live sessions. Along with that, you will be getting lecture notes also in PDF format, which you can download and read it from there. Fine. Now, without any delay, let's get started with today's session. We were doing moving charges and magnetism, and this is lecture number 8. In this lecture, we are going to talk about magnetic field due to solenoid and magnetic field due to toroid. So we'll be discussing about the magnetic field inside the solenoid on the axis. Fine. Using Biot-Savart's law, yes. Later we'll be seeing using Ampere Circuit Law also. But before that, for getting a proper formula, we'll be using Biot-Savart's law. Because for Ampere Circuit Law, if you remember, I told high order of symmetry is required. That means we can only calculate for a solenoid of infinite length. But before that, we should know the formula for magnetic field inside the solenoid of finite length. Correct? So for that, we'll be using Biot-Savart's law. Now, what is a solenoid? You would have studied about it in your 10th standard, right? A solenoid is something, if I take a wire, if I coil it or wind it like a helix in helical shape, then it becomes a solenoid, right? Let's say, and this is a wire. If I coil it in shape of a helix like this, and I connect it with a battery here. So this is the solenoid, where the current will be flowing like this, and in this circular loop, the current is flowing. Correct. Now see, this particular thing, we cannot hang it like this. These wires are so loose, they will fall. So for keeping it in this particular shape only, what we do, we'll keep a base inside it. Fine. It will be a cylindrical base only, and we'll wind the wires around it. This cylindrical base will be a non-conducting hollow cylindrical base, like a cardboard or something. Fine. So if you see, it will be something like this, where this base will be non-conducting hollow cylindrical base. Clear? These wires, the number of turns will be very high. Very high number of turns. Clear? Very high number of turns. So basically they are very closely wound. The winding is done very closely, because of which these wires are insulated. Insulated wires. Clear? The coating will be there on the wire. Because since they are closely wound, they will touch each other, right? Because of which we insulate it. Insulated wires are there. Wires with coating are there. Clear? Now, why we are studying about solenoid in magnetism? See, when we made this kind of setup, when we made this kind of structure, and when it was freely suspended, what we noticed is it is pointing in north-south direction. Every time, whenever we suspend it freely, it will point in a particular direction, and that will be the north-south direction. That means it is aligning itself with Earth's magnetic field. When we change this direction of current, it completely rotated 180 degrees. Let's say it was suspending like this. We change the direction of current. It rotated like this 180 degrees. Clear? What does it mean? It means that this particular setup behaves like a bar magnet. Clear? This setup, when we suspend it freely, it points in north-south direction. On changing the current, it rotates 180 degrees. If you want, you can write that also. It means it behaves as a bar magnet. Note it down so that you remember always. It behaves as a bar magnet. On changing the current, it will rotate 180 degrees. You can note that also. Clear? So basically, we'll be finding magnetic field inside this. This is hollow, right? This base. So inside this base, how much magnetic field will be there in that hollow part? We'll be seeing that magnetic field. We'll be learning to calculate that magnetic field. All right? Now, what you have to remember always is N is equal to number of turns per unit length. Clear? See, later on infinitely long solenoid will also come into picture. So we cannot learn the formula in terms of the length and number of turns, because then the number of turns will also be very high. Infinite number of turns. So what will we do that time? So for that, we will only be seeing number of turns per unit length. That in a unit length, how many turns are there? Using this, we'll get the formula. This particular thing you'll see in the formula, not number of turns, not the length. Number of turns per unit length. So for this, if let's say the radius is R, the length is L, N is equal to N by L. For this, clear? For a finite solenoid of finite length, we can write. Normally it will be given number of turns per unit length. Small n will be given. Clear? I hope you have noted it. We'll go further. Now see, the current is flowing, let's say something like this. So it will be in this direction. You reverse the battery, the current will be reversed, no doubt in that. Fine, then it is coming from here to here. Now we have to see magnetic field inside it. For that, what I am going to do is, I will cut this part to show you. I will show you the cross section. If I cut it vertically like this, from here I take a knife and I cut it. So what you will be seeing, obviously this part will be removed. So these wires you will not see. You will be seeing a current which is coming out from here and going inside here. See, in this circular loop, the current is coming out from this top and going inside this bottom. So if I cut this part, you will be seeing something like this. I have cut it. This is a cross section. Current here, it is coming out, here it is going in. The circular loop is like this, current is flowing. So from up, it is coming out, from down, it is going inside. Correct? Something like this. From here, current coming out, from here, current going inside. So now, magnetic field lines which I have to see inside it, what will be the direction and what kind of magnetic field lines will be there? If you remember last session, what I told, if there is a circular loop in which the current is flowing, if you have to take out the magnetic field direction, what you have to do? Curl your fingers in the direction of the loop, then the thumb will give the direction of magnetic field. If you remember, there was a circular loop, the current was there. On this axis, I told you, on both the sides, the direction of magnetic field will be same. So if it is, let's say, going like this, the magnetic field will be in this direction. If the current is like this, the magnetic field will be in this direction straight. All the vertical components were cancelled, only the horizontal components were there. Do you remember? That means horizontal. See, this is a ring only. Here there are n number of rings. That's all. So due to a ring, the magnetic field line which we got was something like this. Correct? So due to n rings also it will be like this. The strength will be more. That's all. The value will be more, but the direction will be same. So if I see straight in the middle, it will be straight like this. As we start going upwards, it will be a bit bent. Clear? Something like this. Something like this. This we have seen by keeping the compass and all also. Fine. But the direction, since the current is like this, from up it is coming out, from bottom it is going down. So if I curl my fingers like this, my thumb is in this direction. That means the direction will be this. Nearly parallel there. Okay. On this part of wire, if you want to see, on this elemental part, let's say this small part of wire. If I see only this part, the current is coming out. So when we were seeing Wyatt-Savart's law, what I told, if a small element of wire is there, if you have to take out the magnetic field, what you have to do, place your thumb in the direction of current, then the curl will give you the direction of magnetic field. Here direction of current is like this, so this curl will give me the direction of magnetic field, that means this direction, anti-clockwise, correct? So from each wire, if I see the current, the magnetic field around it will be anti-clockwise. This is not crossing each other, they are not touching each other. Since they are very close, I cannot show you without touching, that's why it is showing like this. But they are not touching each other. Just like electric field lines, we have already studied about the properties of magnetic field lines, right? Here, the current is going inside, so the magnetic field lines will be clockwise direction. Clear? Anyways, we will not be talking about these magnetic field lines, because later on I will show you that the magnetic field outside this solenoid is zero. We will be only talking about the magnetic field inside it. Okay? This magnetic field. We will be trying to calculate the magnetic field which is inside this. Fine. Draw the magnetic field lines. Now, again, let's say this is something like this. I have to take out. Now we will be calculating. Now we will calculate magnetic field at a point on the axis of the solenoid. Clear? Now we will calculate magnetic field at a point on the axis of the solenoid. So if this is the solenoid, this is radius r. Okay, this entire circular thing is there, the radius is r. This is the axis, I hope you can see this, right? On this axis, I'll take a point anywhere. Let's say I took a point here. So this point, if you see, I have not taken it at the center. I have not taken it at the center. I have taken it randomly somewhere. Okay, just at the axis we have to take care. At the axis we are finding out. Okay, how to do this? So now there are n number of rings. Very high number of rings are there on it, right? So we will be taking out randomly for some small element, then we will integrate it. Clear? From here there are a lot of rings, n number of rings. We will be going, let's say, from here I went at angle at some distance x, and I took a small element, small part of, let's say, thickness is dx. Clear? Let's say thickness is dx. So of ds thickness, I have taken a small element at a distance x from here. Alright. So now from here, if I see this angle will be theta. Correct? If I take any element here, this theta will be small. If I take an element here, this theta will be bigger. That means this theta is also variable, right? This, if I take any element here, this theta will be more smaller. So this theta is actually variable, like this x is variable. Clear? Theta will be depending on x. Make this much diagram. This is a small element dx of thickness dx, which I have taken at a distance x from point P. And if you want to connect this is at an angle theta. You can assume this way also, that at an angle theta we have taken an element. Clear? Now see, in this dx, there will be some rings. There are a lot of rings, infinite number of rings. Clear? At this small thickness dx, there will be some rings. I don't know how many rings. Some rings will be there. Correct? Due to those rings, I have to take out magnetic field. Small, see, this is a small element dx, because of which there will be some rings inside it. Because of those small number of rings, there will be a small magnetic field here. That small magnetic field I have to write first. For writing that small magnetic field, go to that formula where we have written magnetic field due to one ring. Magnetic field due to one ring. If you remember, if there is a ring, let's say the current is flowing like this at a point P, which is at a distance x from the center. This point is on the axis of the ring. If I have to write the magnetic field, let's say the current is I and the radius is R. Do you remember the magnetic field? Last to last session, proper formula we have derived. What was the formula for the magnetic field? B is equal to mu naught into the current in the ring into the radius square divide by r square, 2 times r square plus this distance square power 3 by 2. Array, yes or no? I hope you remember this. I hope you remember this, right? Now from here, in this dx there will be some rings. The current in those rings will tell me the magnetic field here. Correct? First of all, how many rings will be there? See, we know the unit length. Number of rings per unit length we know. In a unit length, there are n rings. Correct? First I'll write n is equal to number of rings per unit length. N is equal to number of rings per unit length. Clear? So in one unit n rings are there. So in dx length, in a unit length n rings are there. So in a dx length, n into dx rings are there. Correct? Now, how much current is there in one ring? I. Simple, right? See, if I connect this with a battery, I current is going here. I current is going here. The same I current is flowing in each ring, I current, right? But at the same time, if you see at once, each ring there is I current, each ring. So in dx ring, in dx length, n dx rings are there. So how much current will be there? N dx into I. In one ring, I current is there. So in n dx rings, n dx I. Simple. See here. In one ring, current is I. So in n dx rings, current will be n dxi. Clear? Why I am telling you this? Because due to this elemental ring, due to this small element of rings, if I want to write small magnetic field, that magnetic field will be mu naught into I dash. Let's say I have to write this formula only. This is due to one ring. This is due to some rings. Correct? There I is I. Here I don't know the I. Because it is not only one rings. Correct? So I have written I dash. Then radius will be the same for each. So this will be r square divided by 2 times r square plus this distance is again x, the same distance I have taken, x square power 3 by 2. This current I dash will be n dxi. In one ring I current is there. There are n dx rings. So in n dx rings, n dxi current is there. So this dB is equal to mu naught into n dxi r square divided by 2 times of r square plus x square power 3 by 2. Clear? This is what dB is. So first, remember, first what we did, we took an element. In this element, how many rings are there? In a unit length n, so in dx length, n dx rings are there. In one ring, the current is I. So in n dx rings, current is n dx into I. Due to one ring, magnetic field is mu naught I r square upon 2 times this, right? So due to n dx rings, magnetic field will be this Current in n dx rings I have written. That current I have written, I have expanded here. Clear? Note it down. Note it down. Now see. Now this is small magnetic field what I got at this point due to this element. I have to get it for this entire thing. So what I'll do, I'll integrate for this entire thing. Now this theta, either I can integrate for x or theta, but theta is easier. From here to here I have to take entire theta, correct? See here now, I hope this will be visible. If I join this particular end, can you see this yellow color? If I join this particular end, or let me take some different color. Alright, if I join this particular end, this will be one theta. And if I join this end, from here only if I take, this will be another theta. See? So now this one will be taking theta 1 and this one will be taking theta 2. This first one, this will be theta 2, this one will be theta 1. Always remember how we are taking theta 1 and theta 2. Okay? This is theta 2. This which we have connected from this end, the first angle from here. From this horizontal only, from this axis only you have to take the angle. From here this is theta 2, from here again connecting to this one is theta 1. So we have to integrate from theta 2 to theta 1. This line is at theta 2, this line is at theta 1. So this entire thing I have to integrate from theta 2 to theta 1. This complete I have to integrate. Clear? So if you see, this integration will be from theta 2 to theta 1. Clear? Now see, inside there is no theta. How we can integrate it with respect to theta? We have to convert dx in terms of theta. Convert dx in terms of theta. Clear? How we'll do this? See this particular diagram. This is x from here till here. This vertical is r, it is the radius. So, and this is theta, the first angle which we took, the random angle, right? From here I can write tan theta is equal to r by x. Tan theta is equal to r by x. From here x is equal to r cot theta. Or yes or no? This x will go this side, tan theta will come this side, r upon tan theta, r upon tan theta. 1 upon tan theta is cot theta. So this will be x is equal to r cot theta. Now differentiating both the sides, we will get dx is equal to r is a constant and cot theta, differentiation of cot theta. D cot theta by d theta, how much will it be? Minus cosec square theta, correct? This will be minus cosec square theta d theta. Clear? This is what dx is. This we have to put here. So let us substitute. Let us substitute this here. So on substituting, what we'll get? dB is equal to, or b is equal to, let's say, because we are integrating this dB. So b is equal to integral from theta 2 to theta 1 mu naught into n into I into r square, and dx I will substitute by this mu naught into n into I into r square into minus r cosec square theta. Correct? See, mu naught n I r square, mu naught n I r square, and this dx r into minus cosec square theta d theta. Divide by 2 times r square plus x. X also I have to substitute. X is r cot theta. So here r square cot square theta. So this will be 2 times r square plus r square cot square theta. Power 3 by 2. Correct? Alright. Just check everything is correct. Now see. From here, again integration from theta 2 to theta 1. This will be, minus sign will come out, mu naught into n into I into r cube cosec square theta d theta divide by r square is common. It will come out. Once it comes out, power is 3 by 2. So r square power 1 by 2 is r and power 3 is r cube. R cube will come out 2r cube. Inside it is 1 plus cot square theta. If I take out r square common, it will be 1 plus cot square theta. 1 plus cot square theta is cosec square theta, right? Cosec square theta power 3 by 2. Cosec cube theta. This will be cosec cube theta. I'm not going to show you each and every step. That is mathematics. You should know it. Okay. So now cosec cube theta. From here, if you see, this r cube is cancelled. Cosec square theta, cosec cube theta. So in denominator, one cosec theta will be there. Correct? This will be cancelled like this. So in denominator, one cosec theta is there. This cosec theta, once it goes in numerator, it will become sin theta. So what we'll get? Minus from theta 2 to theta 1 mu naught ni sin theta d theta divide by 2. Mu naught ni by 2 sin theta d theta. This entire thing is constant. We can take it out. Integration of sin theta d theta is minus cos theta. Correct? So this will be minus mu naught ni by 2 minus cos theta. And the limits are theta 2 to theta 1. From here, if I put the limit, this minus will come out. Cos theta, limit theta 2 to theta 1, cos theta 1 minus cos theta 2. So mu naught ni by 2 cos theta 1 minus cos theta 2. This is our formula for magnetic field. This is our formula for magnetic field on the axis of a solenoid, of a finite solenoid. Clear? Note it down. Very, very important. B is equal to mu naught ni by 2 cos theta 1 minus cos theta 2. I hope you remember what is theta 1 and theta 2. Theta 1, theta 2 is the first angle, theta 1 is the second angle. From this horizontal, anti-clockwise we are measuring everything. Clear? Got the derivation? This derivation you have to do it again on your own in your copy after this session. Clear? Now, let's see a small question. Magnetic field at point P on the axis of the given solenoid. So this is point P, somewhere on the axis. I have to find magnetic field. Current I is flowing, okay? Current is I in each ring. Current I is flowing in each ring. Basically, it is connected to a battery like this with an I current. All right. So B is equal to, just now we saw the formula, mu naught ni by 2 cos theta 1 minus cos theta 2. Very simple. Here, what will be theta 1? Theta 1 is equal to, theta 1 is equal to, I'll write here, 60 degrees? No. Theta 1 was this angle, correct? This was theta 2. This was theta 2. This was theta 1. Always remember. So this theta 1 will be from here. Don't write again 30 degrees. No. Theta 1 is 180 minus 30, that is 150 degrees. And theta 2, 60 degrees. Put these two thetas, you will get your answer. What is cos 150 degrees? Cos 180 minus 30 degrees, that is minus cos 30 degrees. Minus cos 30 degrees means this will be mu naught Ni by 2 minus cos 30 is root 3 by 2 minus of cos 60 1 by 2. So a minus sign will come out. Don't worry about the minus sign. This minus sign will come out. This will be minus mu naught Ni by 2 by 4 root 3 plus 1. Don't worry about the minus sign. Minus sign only indicates the direction of the magnetic field. Since direction, we are seeing the direction from the hand, right? From the right hand rule, there is no need to write this minus sign. You can directly write the mod of B is equal to mu naught Ni by 4 root 3 plus 1. You can write like this. Not a problem. Okay? Easy question. Now we come to magnetic field on the axis of an infinitely long solenoid. So till now we have seen the solenoid of finite length. Now we will be seeing solenoid of infinite length. Basically, this solenoid is an ideal solenoid. This solenoid is an ideal solenoid. Okay. Here, why it is ideal solenoid? Because it is infinitely long. See, any solenoid cannot be infinitely long. Infinitely long means L is very greater than R. That means length is, on comparing with radius, length is very large, right? Very long it is. That means it is basically a thin solenoid. If I make a solenoid very thin, so this radius ultimately will become very small on comparing with this length, right? So this is an infinitely long solenoid. Clear? Radius will be in, let's say, 1 millimeter, 2 millimeter. This length will be, let's say, in 100 centimeter, 1 meter. Correct? So that is what infinitely long solenoid means. So whenever this will be the theme, L is very greater than R, that means it's an ideal solenoid. And this solenoid is there in your course. Okay, you will not get much questions from a finite length solenoid. 90% of the questions in your syllabus are from ideal solenoid. Okay, they will not write infinitely long solenoid. Maybe they will write ideal solenoid. Sometimes they will not write anything. They will only write solenoid. Until and unless they are mentioning as a finite solenoid, don't consider it as a finite solenoid. You have to consider it as an ideal solenoid that is infinitely long. So you have to remember the formula for this solenoid, what we are going to get. All right. So let's say it is a long solenoid. Radius is R. At some point P, I have to take out the magnetic field. So since it's a long solenoid, formula we know, B is equal to mu naught I upon mu naught Ni by 2. Sorry. Mu naught Ni by 2 cos theta 1 minus cos theta 2. Correct? From here, what will be theta 1 and theta 2? The main thing is to get theta 1, theta 2. Since it is infinitely long, this will be somewhere at infinity, let's say, for this particular point. So if I join this from here, from infinity, if I take this from here to here, this angle will be around 180 degrees, tending to 180. I have already discussed this point before also. If it is, let's say, infinite, from this point, if I try to connect the end, it will be like a straight line, 180 degrees, correct? So this particular angle, if you try to see, this will be nearly 180 degrees. And here also, since it is infinite, if I try to connect this like this angle will be nearly 0 degrees. Clear? Since it is of infinite length, this complete line will be a straight line connecting both the ends. So it will be nearly 0, this will be nearly 180 degrees. Clear? So just put these values in the thetas. So this will be cos theta 1 let me write theta 1 is equal to 180 degrees and theta 2 tending to 180 degrees and theta 2 tends to 0 degrees. Putting these two values here, cos 180 degree, cos 0, B is equal to mu naught Ni by 2 cos 180 degrees minus cos 0 degrees. That is equal to mu naught Ni by 2. Cos 180 degrees is minus 1. Minus 1 minus of cos 0 is 1, that is minus 1, that is minus plus. So minus mu naught Ni by 2 into 2 or minus 2. Clear? Okay. From here, this 2 will be cancelled. We will be getting minus mu naught Ni. Again, minus sign indicates the direction. Since for direction we are using right hand rule, so we do not need to write this. We can write B is equal to the magnitude mu naught Ni. very important formula. रात की 2 बजे भी ये formula याद होना चाहिए. Clear? Very important for solenoid. In questions, 90% of the questions you have to use this formula. Done. For infinitely long solenoid, in bracket if you want you can write L is very greater than R. N is number of turns per unit length. Note down. Next. Now here this magnetic field is inside this solenoid. At the edge, if I want to take, see this point can be anywhere on this axis. Since it is infinitely long, the answer will be mu naught Ni. But exact at the edges, the answer will be something different. Clear? This formula for magnetic field is at any point on the axis. This, if you want to write at any point on the axis except at the edges. Edges means exactly, except exactly at the edges. Clear? Exactly at the edges. So apart from edge, any point on the axis, if you see, the formula will be mu naught Ni. But exact at the edges, the formula is different. Just see. This is a solenoid, radius R, point P. Exact at the edge. Now exact at the edge, if you see, obviously this particular part is infinitely long away. So this, if you see, it will be 180 degrees only, no doubt in that. Nearly equal to 180 degrees. Correct? But this, if you see, it is at the other end. So if I connect this other end, if I see the angle of from here, from the horizontal only we see the angle, right? This angle is 90 degrees. From horizontal, if I take the angle for this, it is 90 degrees, and for the other one, it is complete 180 degrees. So here, basically, theta 1 is tending to 180 degrees. Theta 1 is tending to 180 degrees and theta 2 is 90 degrees. Using this, B is equal to mu naught Ni by 2 cos 180 degrees minus cos 90 degrees. Now if you see, cos 90 is 0, cos 180 is minus 1. So this will be mu naught Ni by 2 with a minus sign. Since minus sign indicates only direction, so if you want to write magnetic field, it will be mu naught Ni by 2. Again, very important. Sharp at the edges. Sharp or exact at the edges. Both the edges, either this edge you are talking about or this edge you are talking about. Exactly at the edges it is mu naught Ni by 2. Mu naught Ni by 2. Clear? So if you see the graph, if I make the graph, this graph is B versus the length of the solenoid. Okay. So now let's say the solenoid, my L by 2 is here, minus L by 2 is here. So solenoid is of L length, which I have kept from the center. Okay. Like this. For this solenoid, if you see, I told any point except the edges, the magnetic field will be mu naught Ni. That is constant, right? For an infinitely long solenoid, magnetic field inside the solenoid is constant. Always remember. Okay, that is mu naught Ni. So for this graph, if you see, from here to here, it is a constant, let's say B. But the moment we come to the edges, it drops down suddenly and it becomes B by 2. At this exact edge. Okay. It becomes B by 2. Clear? It is not that sharp, but we show it sharp. That sharp at the edges, it drops to B by 2. Rest in the entire solenoid, it will be constant as B. I hope this is a straight line. If not, you draw it straight. Alright. Okay. So now if I see the magnetic field lines for an ideal solenoid, since the magnetic field inside it is constant, that is uniform magnetic field, inside this it will be a straight line. Inside this it will be straight line, at which is equidistant from each other. Straight line which is equidistant from each other, uniform magnetic field. At the edges it will start bending because it reduces at the edges. Clear? Inside, uniform magnetic field. At the edge, half of what is inside. Outside, very important again, outside the solenoid, magnetic field is 0, or I'll write 0. Outside the solenoid, magnetic field is 0. Here, anywhere you see, there is no magnetic field. Clear? How? Very simple to understand. Remember the first slide, what I told is here at the edges, here at this wire, if you see, the magnetic field is like this, correct? Current is coming out. If I curl it, so this will be an anti-clockwise. Here also this will be anti-clockwise only. For everything it will be anti-clockwise. So if I take these two, just see. Here the magnetic field is anti-clockwise, here also the magnetic field is anti-clockwise. Correct? Here if you see, this is going upwards, here if you see, this is going downwards. Magnetic field at this point, if you see, obviously the strength will be equal because the current flowing in this ring is I. In each ring the current is I. So the magnetic field strength both will be same. The value is same, but the direction if you see is completely opposite. At this point, at the center, here if you see, here, the magnetic field if you see, it is completely opposite. So it cancels each other. So here, there is no magnetic field outside of this solenoid. Clear? You can understand this way. Done. Next, magnetic field on the axis of infinitely long solenoid using Ampere Circuit Law. So now solenoid is over. Formulas are only this much. We have got everything. This is just the revision of the same formula by a different method. Since it is Ampere Circuit Law, we know we can use it only where there is a high order of symmetry. So we'll not be using this to calculate for a finite length, because for finite length, not complete symmetry is there. If I take a finite length, if I take point here, this angle will be different, this angle will be different. But for an infinite, I can take P anywhere. Both the angles will be, one will be 0 degrees, one will be 180 degrees, correct? Anywhere. Since it is infinitely long, I can take this point anywhere, it will come at the center only. Fine. So using Ampere Circuit Law, we are going to derive. Let's say this is a solenoid. The current is flowing like this in this solenoid. Radius R, point P here. Before calculating from Ampere Circuit Law, keep in mind one thing. This is infinitely long solenoid. That means all those things which we have assumed for infinitely long solenoid, we have to assume here. What all things? First, assumptions. First one. Magnetic field inside this is uniform. Magnetic field inside the solenoid. Clear? Direction for this, if you see, it is something like this, correct? Straight lines. Uniform means straight lines equidistant from each other. Straight line equidistant from each other. Second is very high number of turns. All right. Very high number of turns. Third, L is, since it is infinitely long, L is very greater than R. Clear? L is very greater than R. These are the assumptions what you have to keep in mind while doing this. Magnetic field is uniform inside, very high number of turns, L is very greater than R. Now let's see. So what we'll do, first we'll take an Ampere's loop. So here how we are going to take the Ampere's loop, just see. We'll take an Ampere's loop, this P is there, this can be anywhere. So crossing this P, I have to take an Ampere's loop. Clear? Why we have taken it like a square? Because if you remember, Ampere's Circuit Law is useful only when there were three conditions. One, B should be tangential to DL. So now here if you see this square loop, if I take any DL here, this magnetic field is in the same direction. If I take this direction as like this, this magnetic field is in the same direction as DL, tangential to DL. So B dot DL will be VDL cos 0. That is BDL. Clear? That's why. Second, magnetic field should be perpendicular to B. Magnetic field should be perpendicular to DL. Right? So here if you see this DL, in this line if I take any DL, the direction is like this, upwards. And magnetic field is in this direction, perpendicular. So BDL will be, B dot DL will be BDL cos 90. That will become 0. Right? So that's why I have taken this particular loop. We can take any loop keeping all those things, all those conditions in mind. Okay. Now see. So for this, let's say this is a loop A, B, C and D. For this loop A, B, C, D, Ampere Circuit Law says integral B dot dl is equal to mu naught into I inside. Correct? Integral B dot dl is mu naught into I inside. Now, from here, now this integration is for this entire loop. That means A, B, C, D and A. Closed loop it is. So from A, B, C, D, again A. I have to close the loop. So this integration, if you see, these four are different lines. So I have to take the sum first from AB till then BC, then CD, then DA, integration, right? So this will be integral. Okay, let me show it in the next. I have. Fine. Here, if you see, integration AB, this is B dot dl, then plus integration BC, this is again B dot dl, plus integration CD, this is again B dot dl, then plus integration dA, this is again B dot dl. Fine. That is equal to mu naught into I inside. I inside means I inside the loop. Now see this. Let us take out magnetic field for each arm. First AB. If you see AB, is there any magnetic field here? There is no magnetic field. B itself is 0. There was third thing where I told Ampere Circuit Law is useful when B vanishes, when B disappears, when magnetic field becomes 0 at any place, at any point. Here, at each point, magnetic field is 0. So this is actually fulfilling all the three conditions where we can use Ampere Circuit Law. So here, if you see, magnetic field is 0. So first, for this integration, this will be 0 plus BC. For BC, if you see, if I take any small dl here, the dl's direction is downwards and this magnetic field is this side, that is 90 degrees. So this will be B dl cos 90. That will again be 0, not a problem. Plus BDL, this if you see, CD, this CD. Here if I take a DL like this, B and DL both are in the same direction, that is BDL cos 0. So this will be integral BDL cos 0 degrees. Plus, for this DA, B integral DA, BDL cos 90 degrees. That is equal to mu naught into I inside. I hope you got this, how this 90 came. Very simple, I already told you. This, if I take a small dl here, this dl is upwards direction and B is in this direction, that is 90 degrees. Clear? Now see, from here, this is also 0, this is also 0. Only we are left with this BDL cos 0, that is BDL. So integration, B will be outside, DL will be inside. B is a constant. That is equal to mu naught into I inside. Now, how much is I inside? It depends on how many rings are there inside. Correct? Let's say this square loop is of length L. This length, let's say it is L. We know about small n, number of turns in a unit length, correct? So in a unit length, small n number of turns are there. So in L length, n into L. See, in a unit length, n number of turns are there. So in L length, n into L terms are there. correct? In one turn, current is I. So in NL turn, current is NL into I. Sorry. So here this I inside is, how many turns are there inside? Small n into L. So NL into I will be the I inside. B, and integral DL. What is this integral DL? This complete length integrated from C to D. This is CD only, right? Integral DL is complete length integrated from C to D, that is L length only. It is a square loop. So B into L is equal to mu naught into I is N into L into I. Now see here, this L and this L is cancelled. What we have got is B is equal to mu naught Ni. Same formula what we got from Biot-Savart's law for infinitely long solenoid, where we took theta 1 as 180 degrees, theta 2 as 0 degrees. Same formula, B is equal to mu naught Ni. So from Ampere Circuit Law also you can get magnetic field for infinitely long solenoid. Clear? It's same. See, if you take this direction as opposite, not a problem. In Ampere's loop, you can take any direction. Here a minus sign will come. That will indicate your direction of magnetic field. Okay? So you can just write mod is equal to mu naught Ni, mod B. Done. Now, magnetic field due to a toroid. Last thing. Okay? Due to toroid. What is a toroid? Toroid is basically a wire coiled on a hollow, non-conducting hollow circular object, anything you can say. Okay, any circular object is there, it is hollow and a wire is coiled around it, is wound around it. Okay, something like this. So basically this blue part is a circular hollow object. On that this wire is wound, or you can say is coiled. Okay, so this, let's say here the current flowing is like this, so this will be it will come out like this. Okay, like this it is. I hope you understood. So this is basically, if you see a solenoid, it is like this, right? If I take both the ends of the solenoid, if it's a long solenoid, I take both the ends of a solenoid and I join it. I join both the ends like a circle. I'll get a toroid, right? So toroid is nothing but a circular solenoid. Toroid is nothing but a circular solenoid. You can say circular solenoid. Clear? Now, inside this solenoid, we have to find the magnetic field. Basically, we have to find magnetic field. We'll find magnetic field at 3 different points. One point will be inside somewhere, anywhere in this free space, you can see, right? In this free space, at any point, we'll try to take out a magnetic field. Okay, let's say the point is here. We'll also take out magnetic field at any point outside this toroid. Okay, and we'll also find out magnetic field inside this toroid. If I do a cross section like this, inside it is hollow, right? So inside this, we'll try to find out the magnetic field. Clear? What you have to keep in mind is very high number of turns are there. Very tightly wound, very tightly wound. That means n is very high. Clear? Now make this diagram. Now let's take out magnetic field at point P, which is here. Okay, inside there is a free space where we have taken a point. Here we will be finding out using Ampere Circuit Law, because it's a circular thing, right? So from anywhere you see it is symmetric only. Any circular or spherical thing is symmetric only, right? So we can easily use Ampere Circuit Law. Now at P, if I have to take out, what do we used to do? Make a loop around it like this. I have made a loop, okay, of some radius. I have made a loop crossing that point. Now according, see, at P, magnetic field, what does Ampere Circuit Law say? Ampere Circuit Law says, okay, one second, I'll write a bit that side. Magnetic field at P. Ampere Circuit Law says integral BdL is equal to mu naught into I inside. How much I is there inside this Ampere's loop? 0. How much I is there inside? So 0 current is there, correct? So since because all the current is there outside this, if you see outside this the current is there, inside there is no current, inside this loop. So here I inside is 0, since I inside is equal to 0, this will be integration, B will come out, integral dl, that is equal to 0, correct? You can write B dl cos theta also. We don't know the angle because there is nothing. We cannot write magnetic field. dl, if I do integral dl, this will be entire circumference. That means integral dl is not 0 for sure. So what is 0? Magnetic field is 0. B is equal to 0. Clear? Inside this, at this free space, B is 0. B is 0. Note down. Done. Now let's say a point is here outside Q. Here how much magnetic field is there due to this toroid? What we'll do again, Ampere's loop. Let's make an Ampere loop. I hope you can see. This is the Ampere's loop. How much current is there inside this Ampere loop? See, at Q, if I want to write, okay, just a second. Here only I have to find some space. Here I'll write, okay, magnetic field at Q. Integral B dl is equal to mu naught into I in. Now if you see properly, you will understand, here you have to use sum of this. Again I inside is 0. Some people will be thinking, how? There is a lot of current. See how many rings are there, how many circular windings are there. In every winding there is I amount of current. So if capital N winding are there, current should be N into I, right? No, understand. If I make a cross sectional cut like this, if I make a cut like this, what will happen? You will see the current. Okay, how you will see the current? From bottom, if you see from the inner edge, the current is coming out, and at the outer edge, if you see, current is going inside. So basically, if I do a cross section, you will see a current like this. It has to be dot. Sorry. It has to be dot. It is coming out from this edge, right? From the inner circle, if you see. and from here it is going inside. Everywhere it is going inside. So this will be a cross. Got the point? So from inside, from here, the inner edge, if you see, all the current is coming out. From the outer edge, if you see, all the current is going in. Now see one thing, current in every wire is I, correct? So if you see these two, here current coming out is I, current going in is again I. And I told you, if you take an Ampere's loop, if you remember what I told, in this Ampere's loop, let's say there are two currents, one is I1, one is I2. I have to assume one direction of current. Let's say the direction of current I have assumed in anti-clockwise. Okay. Anti-clockwise means thumb will be pointing outward, that has to be taken as positive. So this current will be positive, this current will be negative, right? That means I inside will be I1 minus I2, correct? Now if both are same, let's say I1 and I2 are same, I. So I minus I will be 0. So here, how much current is coming out? The same amount of current is going inside. This I minus I, this I minus I minus I minus I. Entire current inside this Ampere's loop is 0. Clear? I in is equal to 0. Current coming out is equal to current going in. So because I in is 0, again the same thing, B is equal to 0. Magnetic field here is also 0. Got the point? Magnetic field at inside the free space, this free space, here is also it is 0, outside also it is 0. Now we have to find out the magnetic field inside this hollow part. Clear? Inside the toroid. Let's say there is a point. Now this radius also we have to consider, because inside magnetic field will come. Okay? This radius, basically there is a small confusion to people, whether we take the radius till the inner circle or we take the radius till here. Okay? So basically, in case of an ideal toroid will be very thin. Very thin means something like this. Ideal toroid, very thin. So whatever you take R, it is going to be similar only, same. Clear? So don't worry about R. In general, you can understand this R is basically, if you take till here or here, it will be R. Or let's say till the middle, it is R. Alright? It is very thin basically. I have shown you a bit broad. If you want, I'll draw an ideal toroid. Very thin. Clear? So there is no problem in taking R. From center till anywhere, it is R. Okay? Let's say there is a point S inside this. At this point, it is inside, not outside. Okay? If I do a cross section, then at the hollow part, this S is inside. So here I have to take out the magnetic field. Let me just draw the current again. So from here it is going like this. So here it is coming out. And here it is going in. All right. All right. Now see, again using Ampere's law. So what we'll do, we'll first take an Ampere's loop. Ampere's loop will be something like this. Formula, Ampere's law, integral B vector dot dl vector is equal to mu naught into I inside. Now this time I inside is not 0. See, this is the loop. Only the current which is inside this loop is coming out. There is no opposite direction current. Inside, see, the entire current, if you see dot 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 dot, current is coming out. There is no opposite current or no current is going inside. Current is only in one direction, all the currents. Clear? So, I hope you understood that I inside is not 0 this time, for sure. Now, direction of magnetic field we have to see. See, current is coming out. If you remember Biot-Savart's law again, keep your fingers in the direction of current, curl it, then the direction of thumb gives you the direction of magnetic field, correct? So now, current is coming out. Anywhere if I see, let's say I am seeing this down current. Current coming out, curling, magnetic field is like this, correct? At this point if I see, magnetic field is in this direction. Here, let's say at this point I have to see magnetic field coming out, curling in the direction where I have to see where there is a point. I have to see at this point. So I'll curl like this, magnetic field is upwards. Here see, current at this point, let's say I have to find. I'll curl it in this, magnetic field is in this direction. Here if you see, at this point I have to find, current is coming out, curling is that side. This point I have to find. Thumb is downwards. So magnetic field is this. If you see, magnetic field is always tangential. It will come in this circle. And this Ampere's loop, if I take the direction of Ampere's loop like this, I hope you can see. If I take the direction of Ampere's loop like this, see, Ampere's loop direction and this yellow, this blue arrow and this yellow line, both are tangential in the same direction. Same direction, same direction, same direction. Clear? Magnetic field is tangential to my loop. B, magnetic field is tangential to Ampere's loop. So from here, this is integral B dl cos 0 degrees. If you take the direction of loop opposite, it will come as cos 180 degrees, that a minus sign will come. Okay, but then you have to reverse the direction of current also, so minus minus will be cancelled, not to worry about that. That is equal to mu naught into I inside. B will come out, cos 0 is 1, integral dl. B integral dl is equal to mu naught into, how much will be I inside? See how much current is coming out, I. From this wire, I is coming out, I is coming out, I is coming out, I is coming out, I is coming out. If n rings are there, n into I, if let's say number of rings is equal to n. So in one ring, I current is coming out from each wire. If n wires are coming out, that means n into I. Current will be n into I. In one ring, current is I. So in n ring, current will be n into I. Now see, this will be this integration dl. dl is the part of this Ampere's loop. So dl, if I integrate for this entire loop, it will be 2 pi r. So b into 2 pi r r is this radius, correct? That is equal to mu naught ni. So from here b is equal to mu naught ni upon 2 pi r. Very, very important again. You should remember. For a toroid, The magnetic field is only inside, and the magnetic field will be in circular loop actually. Okay, along this toroid, tangentially magnetic field will be in the circular loop. According to current it will be. Fine. The magnitude will be mu naught Ni upon 2 pi r. See again, if you start comparing it with the solenoid, B is equal to, for solenoid, B is equal to mu naught Ni, where this N was number of rings per unit length, is the same thing written, number of rings per unit length. Total length of this toroid is how much? 2 pi r. From here, any point, if I take the total length of this toroid, it will be 2 pi r. Number of rings upon unit length, upon total length. Number of rings upon total length. That is what number of rings per unit length, correct? So this is basically mu naught Ni. Same thing is written. Same thing is written. If you compare it with that, N is equal to N upon 2 pi r. Clear? I hope you got it. Magnetic field is in the circular loops. Again, I am telling you, direction is tangential. Understood? At all the points, inside also, outside also, and inside this hollow part also. I hope you understood today's session. See this session again, revise your topics again, and derive everything for finite length also, for infinite length also, using Biot-Savart's law also, using Ampere's circuit law also, for solenoid, for toroid, everything at all the points. Try doing all the derivations on your own after this session or in the evening. All right. In the next session, we'll be seeing force between parallel infinite current carrying conductors, definition of Ampere, and torque on a rectangular current loop in a uniform magnetic field. Clear? If you like today's session, do press the like button, share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Alright, you can visit our website www.v-learning.in. You will be getting all these live sessions there. Along with that, you will be getting lecture notes also for each and every session in PDF format. You can download and learn from there. So do check it out. Okay, we'll meet up in the next session. Till then, keep learning from V-Learning. All the best.